Okay. Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Michael Birazman. I am from Group 2, Section 5, Hydraulic. I want to present the introduction, study area, and literature of our group project. The title of our group project is Design Drainage System in Kampung Sungai Yap. Introduction. Road drainage system is one of the mechanisms for draining the water on the surface of the road. The water flowing out would drain directly into the nearby stream. Water runoff on the pavement can cause tire and road deficiency. This condition is likely to trigger road accidents that causes injuries. The water drainage should be also discharged to ensure the safety of road users. Besides, the water runoff also comes from the hills along the route. Typically, in wet season, the drainage of water from the hills flows in different directions. If the water drainage from the hill is not maintained by the proper process, the landslide may occur. Landslide will occur when the soil water content loosen and soil structure itself and allows landslides to happen. As a result, the road drainage mechanism is one of the most effective ways to keep ground from falling. Usually, the water drainage supply comes from rainwater. The benefit of using the road drainage system is to prevent the build-up of water. This is the most important use of a good drainage system, as it enables the free flow of water and in most situations may avoid the build-up that can lead to flooding. The drainage mechanism can also avoid the accumulation of standing water, which may encourage the breeding of mosquitoes. The design process includes a combination of hydrology and hydraulics. Hydrological condition can decide the flow at each location in the drainage system. Interaction between hydrology and hydraulic aspect must be considered together in order to ensure that the structure of the road drain is sufficient to capture all the drainage from the road and the hills. For this project, each group required to apply the knowledge of hydraulic to design the size for the chosen drain system. So we need to determine and label the type of drain suitable along the proposed road for CH 0.0 meter to CH 100.0 meter. Other than that, we need analyze and sketch the direction of flow within the drain along the proposed 225-meter long road. Consider the rational method for 20-year ARI event and Kampung Sungai Yap rainfall station. Next is study area. Pahang River plays the role as a main drainage system to drain off the overflowing water resulting from the flooding event. It is the ultimate drainage system to drain the water from its upstream at Cameron Highlands into the South China Sea. Almost every year during wet season, especially November to December, extreme rainfall has caused overflowing of Pahang River. They have led to inundation of the lowland areas nearby. In this study, northeast monsoon is considered as the extreme weather, which will give great impact to the hydrodynamic changes of the Pahang River. The Intergovernmental Panel on Climate Change (IPCC) 2001 defines an extreme weather event as an event that is rare within its statistical reference distribution at a particular place. The extremely high or low rainfall or precipitation leading to flood or drought is an example of a substantial weather risk. Zin and Germain 2010. Monsoon rainfall is the main cause of resulting to flood event at Pahang River Basin, especially during northeast monsoon, which occurs from November to March every year. According to John 1987, monsoon rainfall and winds are the end result of heating patterns produced by the sun and the distribution between land and ocean. Monsoons are also characterized by their seasonality, geographical preference, and their strength. Pahang River is the main channel to drain off water from the inundated area of Pahang Basin to the South China Sea. during wet season, which is caused by the northeast monsoon. Most of the inundation of lower areas of Pahang River Basin were caused by overflowing of the Pahang River. The statistic of rainfall and hydrological factors were calculated in terms of their means for the period from 1980 to 2009. The highest water level recorded at Sungai Yak was 45.36 meter and the lowest was 43.4549 meters. Whereas for Temerloh, the highest water level was 36.71 meter and the lowest was 34.73 meter. The highest monthly total rainfall at Sungai Yak was 254.01 millimeter and the lowest was 106.67 millimeter. At Temerloh, the highest monthly total rainfall was 219.83 millimeter and the lowest was 93.75 millimeter. The main discharge of Pahang River from 1980 to 2009 at Sungai Yak was 845.78 meters square and at Temerloh was 1008.50 meters square. The water level, which beyond the danger level in recent 3 decades, had also been identified. Okay, as you can see, this is the map of the Sungai Yak at Pahang. Next is the literature area. By and large, street speaks to as primary foundation as a transportation development medium for motorized or non-motorized vehicles to person on foot. Execution of street now and then influenced by ways when a jettison isn't working legitimately to coordinate and carry the runoff absent due to inept physical condition, capacity and support. Numerous writing appears critical impacts of rain condition on the recurrence and seriousness of crash amid blustery day. Hence, the perfect seepage framework be able to decrease water that can debilitate the asphalt of the street. Avoidance of water aggregation must fulfill two primary criteria all through its plans, such as must permit least unsettling influence of normal seepage design, moreover must deplete surface and subsurface water from roadway to maintain a strategic distance from the top unsteady water collection. In the event that the waterway expanding, it is basically consists of a few pipelines to deplete water into the waterway isn't, however, completed. In spite of the truth of lacking of seepage framework to overwhelming rain surpasses the standard concentrated. Even though water is basic in our life, it might encounter of seepage issues. Water, moreover, can be disturbance and cause an incredible bargain of peril. In a race to attain great waste framework, the powerful portion amidst plan incorporates the surface, side channels, culverts, check, canal, and storm sewer system. All these components empower to exist water from entering the asphalt, transfer from the travel path to side channels or canal and carry absent from the street. Height of the street surface ought to be decided. In any case of surface characteristic, incline is the primary issue ought to be considered to discover supreme last spot in potential seepage area. Standard for incline must not surpass 2% that will cause disintegration issues. A few inclines outline more than 4 or 5% as it were in seen circumstances. In addition, such seepage ought to be built to control or collect all the precipitation from the street. It moreover known as trench and the estimate must be adequate to manage the runoff water. Culverts are basic common structure in street seepage in arranged to permit the characteristic stream and release surface to over the street. For brief segment, storm sewer exceptionally valuable in zone with soak slants where runoff in disintegrating open deplete is too helpful at crossing point region.
Now I will present the calculation in our project. 5.1 Calculate the sub-catchment area. For sub-catchment area have two types. The first one is the developed area, the second one is the undeveloped area. In our project, our developed area is 0.3906. For undeveloped area is 0.5332. From this figure, we calculate the developed area and the undeveloped area. We calculate the roadside drain and the shoulder drain as the developed area. For interceptor drain, bench drain, and toe drain, we calculate it as the undeveloped area. Besides, we already label the direction of flow of each type of drain. We can see that the green color is the roadside drain, the yellow color line is the shoulder drain, the blue color line is the bench drain, the red color line is the interceptor drain, and the purple color is the toe drain. After we find the developed and undeveloped area, we need to find the average roughness coefficient, which is the C average. The C average is important in this project is because we need to use the C average to find the Q rational after this. In our project, we choose the Chinese 50 to the 275 and we get the C average value is 0.6903. 5.3 is calculate the Q rational. After we find the C average, we need to calculate the Q rational of each type of drain. In our project, we have 5 types of drain. The first one is the roadside drain, second one is the interceptor drain, and the third is the bench drain, and the fourth is the shoulder drain, and the last is the embankment toe drain. And for each drain, we have the left side and right side. But only for bench drain, we only have the left side only. So all this type drain, we need to find each Q average of it. Now is the find formula we use in our project calculation. The first one is the overland sheet flow travel time, which is the T0. The second one is the travel time in drain TD. And the third is the time of concentration TC, which is the T0 plus TD. And the fourth is the average rainfall intensity I. And 5 is the Q rational, which is the C average times with I times with A over 360. Then we will continue with the calculation data. In our calculation, we will use the old formula in the last slide to calculate it in our project. First data is the left side of the roadside drain in channel 50 to 225. For the roadside drain, we will find the L0, S0, S, and L, use the cross section. After this, we will use this data to calculate the T0 and TD. After we obtain the value of T0 and TD, we can calculate the TC and calculate the average rainfall intensity and continue calculate the Q rational. And our Q rational of the left side of the roadside drain is 0.1625. Then the next data is the right side of the roadside drain in channel 50 to 225. It also same step calculation in the left side of the roadside drain. We need to find the L0, S0, S, and L in the cross section. Then we calculate the T0 and TD. Next, we use the T0 and TD to calculate the TC and continue calculate the average rainfall intensity and calculate the Q rational in our right side of the roadside drain. Lastly, we obtain the value is 0.08409. In the left side interceptor drain, we also need to find the L0, S0, S, and L of channel 50 to 225. But differently is we need to find this value from the plane profile. After this, we calculate the T0 and TD. The TC, I, and Q rational is the same calculation as in the roadside drain. And we obtain the Q rational value of the left side of the interceptor drain is 0.08390. For the right side of the interceptor drain, it also same calculation as the left side. in the channels 50 to 225. We need to find the L0, S0, S, and L in the plane profile and then calculate the T0 and TD. After we calculate TC, I, and the Q rational, we can see that the Q rational of the right side of interceptor drain is 0.04898. For the bend strength, we only find it in the left side in channels 75 to 150. And it also same calculation. We find the L0, S0, S, and L first. After this, we calculate the T0, TD, TC, I, and Q rational. And the Q rational of the left side bend strength is 0.007251. For the left side shoulder drain, we find the L0, S0, S, and L in the cross section in channels 225 to 275. And then we calculate the T0, TD, TC, I, and Q rational. Finally, we get the Q rational of the left side shoulder drain is 0.02733. For the right side shoulder drain, we find it in channels 225 to 275. It also same calculation as the left side shoulder drain. We find the L0, S0, S, and L, then we calculate T0, TD, TC, I, and Q rational. Finally, we get the Q rational of the right side shoulder drain is 0.02757. For our left side toe drain, we find it in the channels 225 to 275. And the L0, S0, S, and L for our toe drain is found in the plane profile. Then we same calculation to calculate the T0, TD, TC, I, and Q rational. And the Q rational of the left side toe drain is 0.005032. For right side toe drain in channels 225 to 275, it also same as the left side. Is we need to find the L0, S0, S, and L in the plane profile. Then we can calculate the T0, TD, TC, I, and Q rational. Finally, we get the Q rational of the right side toe drain is 0.004699. After we finish calculate the Q rational of all types of drain, then we need to calculate the Q capacity of it. The first calculation is the left side of the right side drain. Firstly, we need to find the wetted area, wetted perimeter, hydraulic radius. Q capacity is equals to 1 over n times with A times with R power of 2 over 3 times with S power of 1 over 2. Then the Q capacity value of the left side of the right side drain is 14.422 meter cube per second. Then the next one is the right side of the right side drain. We need to find the wetted area, wetted perimeter, and hydraulic radius of the right side of the right side drain. Then we calculate the Q capacity is equals to the 13.72 meter cube per second. For the left side interceptor drain, after we finish find the wetted area, wetted perimeter, hydraulic radius, we can calculate the Q capacity, and the Q capacity value is 13.94 meter cube per second. And for the right side interceptor drain, the Q capacity value is 16.77 meter cube per second. For our bend strength, we only have the left side. Then we also need to find the wetted area, wetted perimeter, hydraulic radius. Then we calculate the Q capacity of the left side for bend strength. Then the value is 1.06 meter cube per second. Then the next one is the left side shoulder drain. We calculate the wetted area, wetted perimeter, hydraulic radius. Then we calculate the Q capacity, and the Q capacity of the left side shoulder drain is 0.26 meter cube per second. For the right side shoulder drain, it also same as the left side shoulder drain. We calculate the wetted area, wetted perimeter, hydraulic radius, then we calculate the Q capacity. The Q capacity of the right side shoulder drain is 0.23 meter cube per second. For the toe drain left side, we find the wetted area, wetted perimeter, hydraulic radius, then calculate Q capacity. and the Q capacity value of the left side toe drain is 12.89 meter cube per second. And for the right side toe drain, it also same calculation as the left side. The Q capacity value of the right side toe drain is 12.37 meter cube per second. After we finish calculate our Q capacity, then we can compare our Q rational value with the Q capacity value. The Q rational value should smaller than the Q capacity is to ensure the drainage does not flooding. In our project, we can see that for all type of drain, our Q rational value is smaller than the Q capacity value.
Now I will present data analysis from the calculation. We use change from 50 to 275 in our project. From the results of calculation, we get the value of Q capacity and Q rational. For left side of roadside drain in change 50 to 225, we can see the value of Q capacity is 14.422 and its value is bigger than Q rational, which is 0.1625. For right side of roadside drain in change 50 to 225, the Q capacity is 13.72 and its value is bigger than the Q rational, which is 0.8409. For left side of interceptor drain in change 50 to 225, we can see the value of Q capacity is 13.94 and its value is bigger than the Q rational, which is 0.08390. For the right side of interceptor drain in change 50 to 225, the Q capacity is 16.77 and its value also bigger than its Q rational, which is 0.04898. For left side of bench drain in change 75 to 150, the Q capacity is 1.06 and its value is bigger than the Q rational, which is 0.007251. For left side of shoulder drain in change 75 to 150, we can see the value of Q capacity is 0.26 and the value of Q rational is 0.02733. For the right side of shoulder drain in change 225 to 275, the value of Q capacity is 0.23 and the value of Q rational is 0.02757. For left side of embankment toe drain in change 225 to 275, we can see the value of Q capacity is 12.89 and its value is bigger than the Q rational, which is 0.005032. For the right side of embankment toe drain in change 225 to 275, the Q capacity is 12.37 and its value is bigger than the Q rational, which is 0.004699.
For the discussion and conclusion part, there are 5 types of drains chosen in this project for the channel along the proposed road. The table show the type of drains and the reason for choosing the certain drainage for this project. For the first type of drain, roadside drain type 2, the reason is the drain are cast in situ and between the proposed road and the higher level of land beside the road. For the second type of drain, interceptor drain type 2, the interceptor drain is needed if the height of land level is higher than roadside, about 12 meters. For the bench drain type 1, the bench drains are required if the height of land level is higher than roadside, about 6 meters. For the shoulder drain type 1, shoulder drain is built beside the road that faces toward lower level of land. Embankment 2 drain type 2, the two drains reduce pore pressures in the downstream face and 2 of the embankment. The roadside drain type 2 with height 750 mm and interceptor drain type 2 with width 750 mm are chosen for channel 50 to channel 275. For the bench drain type 1 with width 300 mm at channel 50 to channel 150. The drain that are chosen for channel 225 to 275 are embankment 2 drain with 300 mm and shoulder drain with 300 mm. These types of drain, including interceptor drains, roadside drains, and bench drains, are used in the area that cutting activity involved, while they are embankment 2 drain and shoulder drain are used for filling area. For the calculation part, since all the drains chosen are cast in situ concrete drain, thus the mining roughness that we use is 0.015. We have assumed that this area will have developed and undeveloped area, thus calculation for the respective area and average runoff coefficient have been done. In finding for estimate time of concentration, only the interceptor drain type calculate for overland flow due to the design of the drain, thus all other type will calculate for travel time in the drain only. Horton's roughness that applied in calculation for estimate time of concentration is 0.045. The table shows the fitting constant that been used for the calculation. For the lambda, we use 65.914, for the k 0.95, for the theta 0.252 and n 0.817 for the average reference interval of 20 years. In this project, a rational method used is a way to estimate flood by computing peak runoff and calculate the discharge rate. Suitable type of drainage system along channel 50 to channel 275 are designed to reduce the risk of flooding in Kampung Sungai Yap. The drainage system is planned based on the cut and fill area in the plan along profile. Based on the result and calculation, all designed for roadside drain type 2, interceptor drain type 2, bench drain type 1, shoulder drain type 1, and embankment 2 drain type 2 has a greater flow rate capacity than flow rate rational. As a conclusion, all the design that has been calculated thoroughly fulfill all the criteria in a drainage system to reduce the risk of flooding in Kampung Sungai Yap.